Okay, good morning, everyone. I'm very excited to introduce our invited speaker today. Dr. Zhou, he's an assistant professor in the data science, applied math and statistics, and computer science department at Stony Brook University. Joe's expertise spans in NLP and ML applications, especially generative models with transformers like LLMs and multimodal models such as vision language models. His work has received lots of awards. His initial early work received an Outstanding Paper Award at ACL, then a Best Student Paper Award at IEEE ASRU, and recently Amazon Research Award. And really, in all my interactions with Joe, I've seen that he carries a very long and deep perspective in this field of NLP because he did a lot of work, if I may say, in classical NLP and also now recently in foundation model era of NLP. And today we are going to hear him talk about what is the future of NLP and AI systems. So, Joe, very excited to have you. Please go ahead.
Cool. Yeah, thanks, Aryan, for a nice introduction. So today I'm going to talk about some personal perspectives for the future of NLP systems. Um, so um, Thanks for, let me try this. I probably made too many slides, so let's see where we can go. Um, so Thanks for the introduction. Again, I'm an assistant professor at Stony Brook. And a little bit background of myself, so that you can also grab my perspective throughout the talk. I was a trained, as I call it, NLP researcher, mostly around the time when people started all using neural networks to do all kinds of NLP tasks, such as machine summarization, machine translation, automatic summarization, and semantic parsing with these end-to-end trained systems like transformers. The advent of large language models obviously have has changed a lot of things and the general research landscape in the field of NLP. So nowadays, I'm interested in anything that's related to language models, large or small, and also these computational method for NLP and beyond as a general data processing approach. So I actually stayed in Chicago for a year before I joined Stony Brook, and I had the great pleasure to visit the UMN campus around 2024 in May, where there was a beautiful weather. Really loved it. Um, the whole research and industry have been developing these generative approaches and build products in a very, very fast pace. So just give you the sense of how fast things have evolved. So what happened over the year, let's say the last year. So we already saw these advanced AI systems started to tackle harder and harder problems like these competition mathematics. For example, Gemini claimed gold medal for these international mathematical Olympic competitions like IMO. So they got the gold medal in 25, and this was better results from 24, where they were already getting the silver medal. In the meantime, OpenAI also claimed gold medal, and some other kind of players in the field all claim different level of achievements with the IMO competition. And before last year of 25, around late 24, so in this piece of news that I collected in September 24, OpenAI released the O1 model, which was the first model in the O series, which was claimed to be able to do advanced reasoning. Um, and since then, people have spent tons of resources to develop these high-end launch reasoning models. At the beginning, even if we had the state-of-art models like GB4o, people found this was a famous example out there online. People found that the models were always failing when telling or counting the number of R's in the word strawberry. And after we got the O series models, for example, this was just from the O1 model release 24, the model was able to uh, count the correct number of R's in the word strawberry with a little bit of thought. This was just a little over 1 year ago, but nowadays this thinking mode has been the standard for all of these major LM products. And later GPT-5 was introduced. And also beyond NLP, there were a lot of progresses. For example, the so-called world model. So this Genie 3 was a product from Google where you can simulate 3D interaction in real time with a generative approach. And World Labs, a startup from the famous Fei Fei Li, also generated some 3D interactive environments to a high fidelity. And also in 25 last year, OpenAI also had the Sora video generation app, which hit 1 million downloads even faster in a smaller period of time than ChatGPT. So history is being made at a very fast pace nowadays. And nowadays things are moving towards agents. So computer use is a very popular future use case for the agents. So Gemini 2.5, and also a lot of recently OpenAI also published GPT 5.4, which was specialized and trained to do computer agent, use agent with higher accuracy. And just yesterday, actually, NVIDIA held their CTC event where they were launching a lot of these new products in agents and Nemo Cloud, which I believe everyone heard about OpenCloud, which was something to personalize your AI and control your computer and do all the tasks automatically. So there are a lot of discussions and claims of what the future would become as a native AI system integrating all these different components is joined upon us. So these are all very amazing. And we had never been so close to the machine intelligence that can understand, interact, and generate information like us humans. And a lot of these fantastic progress actually came from industry, as we just saw from these examples. But also in the research landscape, perhaps one of the most influential research products in the last year of 25 is the release of DeepSeek R1, which was from January 25. So what was amazing about this paper was that they first demonstrated that reinforcement learning, or RL, actually works for language models at a large scale. So this is a main result figure from DeepSeek R1 paper where they showed that you just need to train the large language model with an and reward. And then the model automatically developed these longer reasoning chains intermediately before generating the final answer. And they also observed inside these ever-growing reasoning chains, there are these aha moments where model discovered moments where they would introspect or validate or go back to backtrack the previous steps to make self-corrections. And this was a very big thing because before DeepSeek R1, everyone was guessing how OpenAI O1 was doing and how they collected data to supervise the process of reasoning. But after DeepSeek made R1 published, it seems to be directing us to a different route where we can just design better reward at the end signal and train the model with reinforcement learning. So they showed that RL actually works. And also the company as a whole has a good engineering effort to do extreme optimization for efficiency, such as proposing the GRPO algorithm as a replacement PPO for faster training and memory save. And also they made their effort fully open source, which greatly helped the research community, LM, and NLP, and general AI as a whole. So in fact, over a year's time, RL has become a standard procedure for LLM development post-training. So I was so interested in this ever since I saw DeepSeek our paper. So I ended up making my own project in my GitHub online to just keep track of these fast-paced progress post DeepSeek R1 of all these amazing RL efforts when they applied to LLMs. And this completely changed the tide of AI research. So 1 year ago, before 25, everyone was talking about process reward models after the OpenAI released their O series, where people guessed that you have to collect a lot of intermediate annotations to supervise the model to learn the reasoning. But now everything goes towards the reward design. So they proved a simple recipe where you design this outcome on verifiable reward plus some reinforcement learning training, and then you can elicit these advanced reasoning as well. And before 25, everyone was talking about training time scaling. Now we had the new paradigm of test time scaling. And this continues to prove to be true when you stack more computing resource during the inference, you continue to get better performance. And over a year ago, we had a lot of discussion about knowledge, high-level reasoning, retrieval augmented generation, and so on. Now we're tackling harder problems such as advanced reasoning, math, coding, and more complex agents for long horizon tasks and so on. And before a year ago, everyone was rushing the game for building better base model and instruct model, and now everything is about thinking model. And so this is a big game changer just over a year. And even what's even more interesting is that in the DeepSeek R1 paper, because their RL trained outline was of also a giant scale, they actually distilled the R1 to the Queen model, which was from Alibaba, another Chinese LM player. And they made also publicly available these distilled smaller Queen models so that people can use them for research and everything, academia and industry. This was so influential in a way that Quinn nowadays becomes one of the most popular open source large language models that we use to do research compared to what was the most popular options, including Llama and Mistral, just over a little bit over 1 year ago. And in fact, if you look at the trend from Google search, you can see that there's a surge of the Queen AI since January 25. And that was because of the DeepSeek R1 model. Actually, DeepSeek made Queen great again, and even more so influential than the DeepSeek models themselves. And so these are all amazing. And also we see that the application, the AI LLMs go beyond the language applications. For example, if you look at this benchmark called GQPA, which is a graduate level Google-proof QA benchmark for science domains like quantum mechanics and so on. And the advancements are so fast that also within a year's time, the accuracy on this benchmark went from about 30% to close to 90% to approach human levels. Actually, this paper was published in 24 and it got one of the outstanding papers in the first iteration of a column conference. But at the time, the benchmark was already close to being solved with a new release of OpenAI O series models. So before we dive, we think about what the future could be like. Maybe we could also go back and revisit a little bit about the history of large language models. Because the research and development of these language models actually spans decades in natural language processing and cultivating in the advanced AI system of today. So for example, we had the first neural probabilistic language model from 2023 from the lab of Bengio. And at the time, it was just simple multi-layer perception, natural language, multi-layer perception, or MLP neural network on n-grams with a limited context window and small size. And in 2013, we got to see word2vec, which was the first large-scale pre-trained embedding model for the static word representations so that we can start working with representation vectors more systematically other than symbols in natural language. And then we got the seek-to-seek models with attention mechanism where people started to train these models end-to-end for doing hard tasks like machine translation. And in 2017, there came the first pre-trained neural language model called Almo from AI2. Their idea followed the word-to-vec idea, where word-to-vec, where we pre-train these static word embeddings. But for Almo, the claim was that we can use much larger data to train these embeddings so that they're contextualized with the context. So the embedding changes with the context. Here, this was a paradigm shift because now we started to train these models of representation extracting devices, which is the so-called pre-trained language models later. And the famous attention is all you need paper or the transformer architecture was also proposed in 2017. And then we got BERT, GPT, GPT-2, GPT-3, which was first leap in the size of these models from OpenAI. And then we got Interact GPT, which laid the foundation of the product of ChatGPT, where we saw this trend of these technologies in NLP and large language models can first be translated in a real world product where you can use human preference data and reinforcement learning to tune these models to build these chatbots that can please and solve questions of human beings. And then we saw the release of these products, and then since then, there came into the period of racing between all of these companies, and people build these more and more advanced products and LLMs with a even shorter period of time. So, and then 25, we got DeepSeek R1, and now we're in an era of using a lot of reinforcement learning to post-train the large language for advanced reasoning agents, and a lot of these end-to-end tasks where traditional gradient based approaches were not very convenient. So each leap builds on data, compute, and prior techniques, but the time between these leaps are shrinking exponentially. So what is NLP anyway now? Traditionally, we roughly before ChatGPT and LLM, NLP was structured as different subfields for different tasks. For example, we had a lot of people working on text classification, specific techniques for document summarization, for machine translation, for language modeling, and people build conversational systems with NLP and also question answering systems. So each of this box was a subtask, and we had specialized tools and techniques to do all these tasks. And language modeling was just one of these subtasks in NLP. But now everything can be solved with language modeling. So NLP has gone from dealing with this individual tasks with different techniques to now was simulate a unified technique called language models to solve all these tasks. So once NLP meant a collection of these narrow tasks, but everything today is about language modeling. And this is also the so-called LLMs and even synonyms of AI nowadays. And this is so influential as a change of trend, because the number of publications, if we see the data about large language models by year, we can see that this actually grows exponentially after the large language model became popular. And these are grouped by different source of venues of publication. And from this Nature paper, you could also see that since the ChatGPT launch, um, the growing number of papers not only is not only in the field of computer science, but they actually expand to all different fields in science. And this is there's even a new conference started in the year of 24 called Column, Conference of Language Modeling, which was organized by my advisor, Sasha Rush, and also many other senior folks in the field of NLP. So, and within the past 2 years, we already had two gatherings of the conference of Column. We saw great applications moving slightly different from the traditional NLP field. So, why language modeling? The explosion of language model builds on data, compute, and prior techniques. So here I'm going to talk about a few important pieces that made language model become the de facto device or technique for solving all these NLP tasks nowadays. Um, so we all know that language models, modern language models, at least operate on these next token prediction technique, where when you have a sequence of tokens, you would generate them one token at a time by decomposing the joint probability to the sequence of predictive probabilities. And this is an extremely simple mechanism for modeling the language and also for generation of the language. And with this, everything of the traditional narrow task can be formulated as a generation problem. For example, text classification. Previously, we designed a specific method for doing text classification, such as having some classification heads or doing multivariate classification with neural networks. But now this can be cast as a generation problem. You can just generate the label. You can also do document summarization where you put the prompts of the source document and let the model generate the summary. You can do machine translation, conversation, so on and so forth. So this is a single learning objective and generation paradigm that can unify the entire field of all these different tasks, extremely generalizable. And second, we had the transformer architecture. This may not be the unique architecture that can work well, but it was architecture that unlocked the scaling laws, going from RNNs, which we were using for language modeling before transformers, to these attention-based transformers. We allow better or scalable parallelism for training. So now we can have this device or technique to try out more scaled up data, compute, and training. And third, it's probably about the same time because we already had, since the invention of internet, we already have decades of accumulated digital text and multimodal data from the whole internet. And also we have built these massive compute capabilities with these optimized hardwares from CPUs to GPUs to TPUs and also all these custom accelerators. So with these infrastructure and giant vast amount of data, we're able to produce the product large language models. So if we think retrospectively, it's probably not a surprise. Now we have large language models because when data, compute, and architecture, and also this simple paradigm of next token prediction are all aligned, so this emergence can happen. So when the right objective met the right architecture at the right time, so now we have language models which become AI's universal substrate. And so here's a bit of illustration of what has changed in NLP. So traditionally, NLP is a subfield, at least of AI, and language modeling was just a subtask. now. So the task of language models actually occupies a large size of NLP and also sometimes becomes synonyms of AI. But there's still a lot of challenges, right? So even if these things are so amazing and it seems to solve all kinds of problems, um, we have a lot of remaining questions in the field, so that we can visit them and also we can think about what we should work on for the future. So, for example, there's unprecedented speed of change. So within a year's time, the world has already changed so much, and the research half-life has been greatly shortened. And what was state of art last semester may now become obsolete. And we have escalating computing demands. Research in this field, at least in large language models, increasingly are gated by these access to compute and infrastructure. And also, the knowledge foundation has shifted. For example, a lot of universities, people are talking about redesigning the education in computer science and AI because the field boundaries are more and more blurred. NLP, so as an NLP researcher, I now also work a lot on multimodal data and reasoning and multimodal language models because they all use similar devices of models. And also because of the fast pace of research and product, there are a lot of challenge in the societal impact and also in academic research. And education, publishing, reviewing, funding cycles move much slower than the technological curve. So I'm going to discuss some of my personal perspective of the future of NLP, or some things that I think we can still work on in this very challenging time. I'm going to discuss NLP, but a lot of these are now become the so-called LM research, and also you could also call it AI systems, because people are not very careful, and notion of NLP becomes also very obsolete nowadays. So, in order to know what we could still work on in this transformative era, so I tend to think about what a future AI system could still benefit from research. So here I list the three general ideas that we can still work on, forward-looking what the future AI system could move towards to. So one, I think the future system could be more efficient. This is an ongoing effort, and I think there's no stopping to the efficiency research because whatever we use, we could always make it faster, more efficient, serving better of the users. And I think the future system should be continuous to be multimodal. So we went from natural language processing research in language models. Nowadays, these models seem to be doing well, processing data from all different modalities like images, videos, and audios. And really, the language models are becoming a general learning tool for sequential data, not only language. And third, as these models continue to be deployed in real world, we really need to consider their safety or trustworthiness and their real indications of the society. And also, we probably also want to build more and more personalized systems. The way how OpenClaw was so popular was also part of the need of people having higher and higher demands of this system to be personalized to their own workflows. So I'm going to illustrate a few research that we have done in the past 2 years since my graduation, because that was also a big paradigm shift for myself, going from a traditional NLP researcher to a more broadened view of language modeling research. I'm going to talk about different research pieces for each of these challenges. And then at the end, we can see what we can still build for the future of NLP or LLM or AI systems. So first, I think the future AI system should be still be more efficient. So we all know that these language models generate tokens one at a time following this predictive probability. Um, and For N tokens, there's an intrinsic limitation of how the LM operates. So you have to run the language model N times through all the stack of layers internally. Potentially, this model is very big. You have to run it N times sequentially. This is a hard limit of the speed of this language model generation. But if you see how we interact with these language models, for example, if we interact with ChatGPT and we ask similar questions over and over again, for example, here I ask, "What's the answer to life in the to life, the universe, and everything?" The answer is always 42, according to the book. And the model may generate different phrases or different expressions of the sentence around the same topic. But the key information, like is 42 Douglas Adams and the book's name, are always the same because these are just the same knowledge. But model still has to generate all these tokens one by one, even if through repeated interactions, it will always give us the same answer because they're just the true answer. So why? So this prompted us to think, why does the model need to generate the same text token by token and every time, even if we know they're going to be the same? So imagine if you interact with ChatGPT, every time it generates, "Thank you very much." It may be 5 tokens, but model has to generate them always one token at a time. But maybe if the model already starts to generate "thank you," you can already know next 2 tokens will be very much, and then you can directly output them instead of generating from the model. So this is essentially the idea that motivates the work I'm going to talk about in the next. So another aspect of motivation is that what if the knowledge changed? So even if you ask the same question over and over again, if the question is based on the dynamic world, it may change, right? But once the LLMs are pre-trained, the knowledge becomes stale. And we can only use techniques like retrieval augmentation or search to augment the knowledge during inference time to make the knowledge more dynamic. So based on these motivations, we propose a simple solution. How about we can extract these text chunks and store them along with their context in a database. And then when we are at the inference time, we can directly generate these chunks of multiple tokens at one step by retrieval. So here the key is the multiple tokens, because if we can retrieve multiple tokens, that can skip the model computation for token by token autoregressive generation. So extracting the text chunks, so this deals with the quality of the generation, and multiple tokens at one step, this deals with the efficiency. And actually, in our preliminary study, so this is a visualization of probabilistic probabilities of the tokens in a consecutive sentence of the answer to life, the universe, and everything is 42 according to the book. We can already see that internally the model already have some sense of these local knowledge by gluing all these tokens together with the high plateau of probabilities. So maybe if we start to generate the starting sections of the book, we can already predict what's going to be next with no loss of accuracy. So this is how the proposed chunk distilled language modeling works. So first of all, we have some documents, and we can run the documents through the model. And then we can save a chunk database. So we can discover these chunks by just looking at these model probabilities when we run the model on the document. So whenever there are consecutive chunks of high probability, that means the model, given the context, has a very good sense of this should be a unit of knowledge, and we can store these knowledge in a database. And then at the inference time, so this can build a self-memory because the chunk is discovered by the model. And at the inference time, we can let the model generate, and then at different places, we can go back to the chunk database and see if the context matches the chunk context. And if it matches, we can directly retrieve the local information from the database is 42. So this way you can save these two steps of generation from the model, and this improves the efficiency. But how about quality? So if we discover the chunks from the model itself, this is so-called self-memory. So the model will generate the same information from its own memory. But what if we want to extend this information? So again, we have a document. We can use a better model to extract these chunks. So this model will be different from the model we use for inference. We could also even use human expertise to extract these chunks. So this will make this chunk distribution of knowledge different from the base model distribution. And when we inject this database information back to the model at inference time, this would also have the potential to increase the quality of the model. So depending on where the knowledge is from the model itself, from a better model where we're similarly doing knowledge distillation, but not with training, or from human beings, we can have these different variations of this proposed chunk distilled language modeling approach, or CDLM. And some of you may working in NLP may already know some of the techniques called speculative decoding, which is focused on speed up generation, and retrieval augmentation, which is focused on injecting dynamic knowledge to LLMs. So compared to them, so our proposed work CDLM can also speed up generation. But retrieval augmentation does not speed up generation. It just injects knowledge. And also, in terms of knowledge improvements or distribution improvements, speculative decoding is a pure inference time acceleration algorithm that does not improve the distribution. The whole point is to keep the distribution LM intact with acceleration. And retrieval augmentation can improve distribution by injecting new knowledge. And so can the proposed CDLM. So, so this is a rough idea of the algorithm. Here I'm gonna show with a little animation of how this actually works. So basically, we store all these discovered chunks in a database organized by tries or prefix trees for efficiency, and then we let the model generate at inference time. So model will operate token by token, but at every step we actually check some kind of contextual match of the current context with each node in the try database. And if there's a match, and then we would directly fill in this chunk into the generation. And so that we can skip all these generation that we retrieved locally, fine-grained. And then we continue the process. And if we have another match, we can skip the next few steps of generation. The process continue until we reach the end. So this can boost the model inference efficiency without retraining. And then, so here are some main results. I think I'm going to skip most of the detailed results, which you can find in the paper anyway. But here, this roughly shows is that compared to a variant of speculative decoding, which is also based on these multi-token chunks, we can save the average token time and also average the forward passes. And perhaps the generation example here is more telling. So these are the eta is some kind of hyperparameter that controls the frequency of the retrieval. So this is a fine-grained retrieval interlead with model generation. We can see the red tags are actually retrieved chunk, and the other tags are token by token generated by the model. We can see the generation quality is pretty good in this case, and then we can save a lot of compute because all the tokens in the red tags are generated or retrieved all at once without going through the model. And so beyond just accelerating the inference, when we discover the chunks from better models, so this is essentially doing knowledge distillation through the intermediate chunk database. So if you compare the perplexity of our approach, KCD-LM, actually on a general base model with a teacher model from these detailed domains of code, law, and medical, we achieve better performance and lower perplexity. And if the knowledge is from experts, from human beings, for example, in this case, we collect these chunks into a database by treating them as the hyperlinked text directly from Wikipedia passages, because those are marked by human beings already. And then we can run our algorithm where we can show that actually these are chunks ranked by their frequency. So we can show that in our approach, CDLM, it has a higher potential to generate these rare chunks in the actual human corpus. So as to prove that we have actually injected these chunks from human definitions in Wikipedia. So this is a bit of human evaluation results. But overall, so here's a brief summary of this work. So we propose chunk distilled language modeling focused on the inference time efficiency. So it improves both the generation efficiency and also adapts the generation distribution on the fly if we choose to use external knowledge to build the chunk database. Cool. I think I'm gonna continue to the end, so we can save all the questions until the end, because I still have a few things that I wanna talk about. So we talk about efficiency. So here I'm gonna talk about some of the multimodal research that we can do. So basically, the success of LLMs has also opened new space and ideas of processing multimodal data. So here's so previously we had LLMs that can do different tasks, but now the LLM based vision language models, for example, can also serve as a foundation model to deal with different tasks that incorporate visual information, such as object localization, visual QA, captioning, and segmentation, so on and so forth. And here's a typical structure of vision language models. You can see that in this case, the paradigm is to generate text from or generate language from images. You can see that the backbone is still a language decoder, so it's the language decoder. We still have the prompt before generation, but before the prompt, or in some different architectures inside the prompt, we would also have these visual tokens that are processed and extracted from a vision encoder, typically also uses a transformer architecture like VIT to generate these vision tokens, each corresponding to a patch in the image. This is just a very commonly used vision language model architecture nowadays. And for example, if you have an image and then you can generate a sentence describing this image, man is holding a surfboard on the bench. But obviously, in this case, this is probably wrong because the man is holding a clock. So this is another challenge in a lot of these visual language models, which is that the model still tends to hallucinate in that it recognizes the objects or details in the image not correctly. So one research question that we can ask and work on is that how we can still reliably decode from the image so that the generation stays faithful to the image. So we worked on this problem of hallucination reduction in vision language models extensively. So here are just two examples of the work that we had produced in the last 2 years. For the first one was called object hallucination reduction through adaptive focal contrast decoding, or called HAWK. Basically, the idea was the motivation was also very simple. So basically, if we look at this image, if we input the whole image to the vision language model, the model hallucinates a surfboard because the background is the ocean and the beach, and probably there's a strong inductive bias to generate a surfboard from the language models. But if we zoom in and maybe just let the model look at the image of this small area of holding a clock, the model could decode correctly locally of the actual object. And to verify this intuition, we actually did some manual experiments to just using human to identify the optimal visual context or visual window to be passed to the vision language model for the decoding. So here the blue bar is the hallucination rates or number of hallucinations in a data set when we pass a full image, and the orange bar is the hallucination numbers when we manually select the visual window to be passed to the vision language model, and we can see the hallucinations greatly reduced. But at inference time, we don't have humans to monitor or to look at where we can pick the window. So we ended up using a sampling approach. So basically, uh, uh, we pick some small window and then gradually enlarge the window, and then observe the probability of certain objects generated by this ever-changing receptive field. So if you look at the probability of or log probability of the ground truth token clock, you can see as there exists some kind of optimal window in the middle that can decode this correct token perfectly. But if you focus on too much detail or too much background, this will die away. So building on this iteration, um, we propose the algorithm called HOG. So I'm going to quickly run through how this works, leaving all the details in the paper. So basically so this is also inference time algorithm. At every step, we generate a token, and then we take the token back to use off-the-shelf object detector to find some kind of small region that may correspond to the token. And then we can sample a bunch of different receptive fields starting from this small region so that we get a lot of different distributions. And then we can contrast based on this distribution to gather different logits. And finally, use another scoring model to select the best logit to correct the generation from surfboard to clock. So this is a general pipeline. But I think there are a lot of technical details for the inference time, and I'm going to skip the results here, but directly looking at some examples. So basically, here the red marks the hallucinated context from some of these. So Grady is the Grady baseline, and then alpha and VCD are some of these other approaches that were proposed to tackle the hallucination problem. And we can see basically the HOG corrects some of these hallucinations, like display on the wall and so on and so forth during the inference time. And here's another example. So this is a simple example illustrating of how we can still apply some of the language decoding approach with the feature of the visual information to help reduce the hallucination. So another interesting question is, what does these vision tokens represent? Or how do we understand these visual information encoded in the vision language model so that they can be used to decode the text? So here in another project, we directly took this question and then tried to interpret these visual representations, each corresponding to a patch, to the text space. So basically, what this was doing was that we just take the representation after the VIT and the mapping network corresponding to a small vision patch, and then directly project this to the output embedding of the language and see how we can interpret these visual patch or their internal representation to the text space. So you can already see some of these visual representations are connected well to the text space. For example, here you see this is a computer, Mac, laptop, and the book. You have the map, street, and so on and so forth. But also, if we make this projection, we can also check the uncertainty of the projected distribution, and maybe use that also as a signal of how well these visual representations are generated in terms of helping the downstream text generation. So just briefly about this work, we just take this intuition and try to use this distribution of the visual text projection to guide us to drop out some of the vision tokens during inference time that we think has very high entropy or low uncertainty. Basically, we do dropout. We call it dropout decoding because we do dropout during the inference, not during training, and during the visual tokens as input to the language model, not for the model parameters. So this is a kind of randomized visual context, but also to reduce the noise of this kind of context dropout. We ensemble the generation with parallel dropouts and then aggregate their distribution. So basically, this is rough illustration. Gonna skip this. So with the field of multi-model, I think making the model generate more faithful context is still an interesting problem that we can explore. And also we can try to understand better of how these multi-model representations work in terms of language generation and also visual representation or the vice versa. And inside the multimodal research, beyond tackling the generation problem directly, we could also think about even more novel applications. So in these examples, I talked about generating text from images, but we could also maybe think about how the vision language model can help process text. So in this case, can we use multimodal models like vision language models to process text as well? To improve the token efficiency. For example, this is not simply OCR where you have a document of text and then we do the OCR and then pass to the language model. But here we hope to directly use the vision language model to process a document of text directly for the tasks of text classification, summarization, translation, and so on. So this intuition builds on our kind of technical understanding of how vision language model works. Basically, for a language model, so if you have n text tokens, you have to pass these tokens to the LM decoder, and then n tokens will correspond to n text tokens will correspond to n steps. But for images, if you have n text tokens in the image, it does not translate directly to n text tokens to decoder because images are processed in a way that each patch is corresponding to a visual token here passed to the text decoder. So maybe we can save some of the compute or the tokens used to the text decoder when we represent the text information in the image. So in this work, we directly tackle this problem and trying to see if we process the context into the image through vision language model, can we save some of the tokens, context tokens used by the language model without loss of accuracy? So basically the procedure is simple. So we render the text into images. We had an algorithm that can place these texts to fulfill the image on a white background, just like a document. And then we pass the full image to the vision language model. And then we compute the model performance, such as accuracy of a task versus the token efficiency and see, can we save any tokens without loss of performance? So here, so this is the results on GPT 4.1 mini, which is a multi-model model on the task of long context information retrieval. So basically, a task has a lot of context, and the question will be asking you to retrieve certain information in a local place in the context. So each curve represents a setup of different image tokens or different image patches representing the text. And x-axis represent number of text tokens that are rendered in this image. We can see, for example, if for the cases where we use 783 image tokens, the accuracy on these tasks does not drop even to close to 1,300 text tokens. So we can already get kind of a ratio of about 2 for the compression in information here. So here is another open source model. Basically, we got similar results. So these are summarized in this figure. basically access is a vision token, y-axis is a text token. And then each point is a point such that when we use a vision token represent text, the accuracy does not drop. So you can see that with about 1,500 tokens, we can already process the task or the question when the original text token are about 3,000. So we can see that this visual language processing of text consistently compresses half of the text tokens. And so this is a very interesting and very cute finding in kind of merging these modalities, thinking about vision, language, and text processing. And some of you probably heard about DeepSeek OCR, which was a very popular research and product published in October last year. Within just 2 weeks, their GitHub grows to around 20K, which was very hot topic at the time. And also there were a lot of discussions on the internet. So essentially, if you're wondering, so this is essentially the same idea. So our work published in NLP 25 findings. So we're doing that in the last spring, but we were just using off-the-shelf VLMs directly and saw these 2x compression rates observed already with no specific tuning. But with DeepSeek, they further pushed the limits of compression through large-scale training, data collection with architectural changes of vision language models, and they can achieve even further of 10 times compression rates with their great effort. This also showcased difference between like industrial and academic research nowadays due to the differences in compute and resources. And recently, someone even this is another interesting story. Someone even sent me this paper on the right, where the content essentially basically is almost same as our paper published last year, except the authors and title. And they even acknowledged me, my acknowledgement in the acknowledgement. So I think this is just a pure plagiarism. So this is also kind of showcase how kind of odd AI is, but definitely this is not a good way of doing research and writing papers, even if everyone wants to work on large language models in AI. Cool. So I think we're a bit over time. So I still have a few things about trustworthiness and personalization, but we could also stop here and take questions.
Yeah, thanks, Joe. I think it would be great to take some questions from the audience.
Yeah, yeah,
Yeah.
cool.
Questions?
Mm,
So on the slide where you had the prefix tribes,
hmm
uh,
Okay.
how exactly do you match like which branch of the tribe you're?
Yeah, that's a great question. So detail here is that when we save the tribe, for example, if we when we discover these chunks, we run the language model to the on the corpus, and we save this contextual vector inside the language model to associate with each node. So the try actually saves the tokens, the prefixes, and also its key as a context vector or the hidden state inside the language model. So when we run the model, we actually use the current context vector, which is the last layer hidden state, to match the keys in the node, and then we find the max match, and then we retrieve that. So it's kind of similar to dense retrieval, but without separate models for these vector-based keys.
Thank you.
Yeah, does that answer the question?
Uh, if not, I have one question, Joe. I really
Mm,
like this part of your history. When I was looking at, you described how NLP was divided into multiple
hmm
themes, but it seems like it's
hmm
really about how different sub areas have different evaluation practices, and it's more about evaluation. It seems that
hmm
transformers, if I remember correctly, the original attention paper, and other related
hmm
has really come from machine translation as a subfield.
hmm
And
Yeah, yeah, yeah.
was like, what was the special thing about their evaluation practices, or was it just about their more data? Like, why
hmm
from machine translation rather than doc summarization or other things?
hmm Yeah, that's a great question. Yeah, so in my class of NLP, I'm still using machine translation as an example to teach like sequence models and attention. So I think machine translation was considered the crown of NLP tasks because it was very hard. And it was a task with a long history study, even dating back from like 50s from IBM. So yeah, I think one reason is that it was considered hard for all the time. And a second reason is that it has real applications in the real world. Because that was probably one of the direct products that we can use to help people communicate across different languages. And third was that people study a lot of machine learning approaches from the early days for machine translation, including statistical approaches and neural network approaches, also because we had abundant data for machine translation. So there is machine translation workshop and data collection from United Nations Parliament as an example because these are general sources because in United Nations, people generally do these kind of translation to document everything nicely. So throughout the years, we have accumulated a lot of data there for people to explore different approaches. So it was usually used as a test bed for the state-of-art NLP models for many, many years. And also like in real products like Google Translate and Meta also had their translation system. So there was also both the data and also real needs. And also the task was considered like direct tackling language translation as very difficult. Yeah.
Yeah, thank you.
Mhm.
Any advice?
So in the vision language models, what was the vision encoder?
Mhm. Uh, yeah, vision encoder was VIT. So this is a typical architecture called Lava. It was probably old because it was there since 23, I think. Yeah, so the vision encoder is a vision transformer, which is a bidirectional transformer. Like BERT, yeah. But the input is patches, yeah. Sequentialize the image, yeah.
So when you like try to so in your app like have algorithm when you try to like segment the object that's most related to the context, uh,
hmm
how do you like how do you like do that? Like how do you like also like use
hmm
context vector along with the segmentation?
Right, that's a great question. So during the generation, we really don't have a ground truth of where to look at. So the way we did was we had a kind of preliminary generation. So we would first generate a token. Let's say the token is surfboard, and then we would use an um, off-the-shelf object localization or detection model. We use ground dino in this case, and to find the bounding box corresponding to this token. So even if this token is surfboard, it's wrong. We found that in practice, the model could also already identify roughly the region of object like this in the image. And even so, this could be still incorrect. So we then sample a bunch of these receptive field um, centering around this initial box, and then pass all of these in parallel to the model for decoding, so that we get different distributions. And finally, we would contrast this distribution to find the signals that are amplified by consecutive receptive field, and then try to extract those signals as correction for the token. Yeah. It's a bit complex, but I hope that give you an overview or general sense of how we did that.
Have you like tried these methods where there's like, for example, a surfboard and a block,
Mm.
then it's
hmm Yeah, so you have the surfboard, and then we pass this to an object detector, so that we have an initial window, and then based on that, we just sample a bunch of windows around it. So the idea is based on this kind of observation. So these are just a range of these windows, and we just keep sampling this, and we find there are places where if you compare these two windows, the logits out of these two window decoding, you can get larger kind of contrast for the ground truth, like plot here. But for like surfboard and other kind of irrelevant tokens, the contrast is not as obvious. So we hope to use this signal to kind of extract the correct information.
thank you.
Yeah.
So I wonder what's your viewpoint about the diffusion-based language generation?
hmm Yeah, that's a great point. I'm actually also looking at diffusion-based language models. Um, I think on the efficiency side is it's great. So a lot of these I think it's reminds me of a lot of the non-autoregressive generation when transformer models were just coming out in around 2019, 2018, where there was I also work on this a little bit where we just removed the autoregressive constraint and try to generate text all at once for the sequence. So you have to fix the length first and then generate all the tokens at once. And even at the time, it was the most effective approach was also iterative. For example, you just generate once and then you fix the error, generate other time, or doing this unmasking altogether. So I think the limitation was one is that you had to fix the length first. And second is that it doesn't deal with very long context very effectively because you have less coordination between tokens. I think recently, because of large language models and the real need for efficiency, this kind of non-autoregressive generation manifests in the diffusion-based language model paradigm. And out of one popular design is just exactly similar, so that you can do this masking iteratively, and they show great performance boost, like efficiency boost. But I think the long contact is still kind of maybe a bottleneck. So I would imagine maybe in the future you do some kind of blockwise diffusion generation with like between block you do autoregressive kind of semi autoregressive generation where you can generate local information with diffusion and maybe like long-term global information with autoregressive. Yeah, but yeah, we still have to see. And I think another way of doing diffusion is just directly doing the latent space. I think there are also a couple of works on that. I think that could also be interesting because if you do that in latent space, you could potentially even break the tokenization barrier and have more dense representation of the tokens. So maybe that could also be worth exploring further. Yeah.
If no other questions, let's thank Joe again.
One
Oh,
Mhm.
one question. One final question.
last question. Yeah. Hi,
Mhm. Mhm.
I have noticed that some of the works are about the token level uncertainty, and
Mhm.
I think that there might be the overconfident issue in this when calculating the uncertainties. I'm not sure if you have looked at that.
Mhm. Yeah, so I think that's probably a real issue. So I don't really so even if we do this, I don't really think uh if we take the distribution directly and the uncertainty of the distribution can directly um correlate with the actual uncertainty of the hallucination or the model knowledge. So there are many different factors. So in this case, we did not because it's kind of randomized algorithm. we take the distribution, but also we have some kind of random sampling approach to kind of reduce our reliance on distribution totally. And then we also do this randomized context dropout in parallel for multiple rounds and aggregate ensemble the results so that we can reduce the reliance on these kind of whether it's overconfidence or other issues with the distribution itself. Yeah, but I think that's a great point.
Okay, let's thank Joe once more.
Mhm. Yeah, yeah. Thank you so much. Yeah.